This is a Math 3 summary video for the lesson titled U-Mix Cubes. This is a Solidify Understanding task. The purpose of this lesson is for students to compare cubic functions to quadratic functions and identify key features and characteristics of cubic functions. In Scott's March Madness, the function that was generated by the sum of terms in a quadratic function was called a cubic function. Linear functions, quadratic functions, and cubic functions are all in the family of functions called polynomials, which include functions of higher powers too. In this task, we will explore more about cubic functions to help us see some of the similarities and differences between cubic functions and quadratic functions. To begin, let's take a look at the most basic cubic function, f of x equals x cubed. It's technically a degree 3 polynomial because the highest exponent is 3, but it's called a cubic function because these functions are often used to model volume. This is like quadratic functions, which are degree 2 polynomials, but are called quadratic after the Latin word for square. Scott's March Madness showed that linear functions have a constant rate of change, quadratic functions have a linear rate of change, and cubic functions have a quadratic rate of change. The parent function for cubic functions is f of x equals x to the third power, or x cubed. Here's the graph. You can see that it's increasing, and the table, the x values and the f of x values, and the first, second, and third differences. Let's take a closer look at the first, second, and third differences. So the third difference here is constant. The second difference had a constant rate of change, so that means it is linear. The first difference had a linear change, so that means it is quadratic, which means that this cubic function had a quadratic rate of change. Let's look at a few of the key features for this cubic function, f of x equals x cubed. So again, we're just looking at the parent function here. Its domain goes from negative infinity to positive infinity. It's all real numbers. The range also goes from negative infinity to positive infinity, so the range is all real numbers. The x and y intercept are right here at the origin. And the interval of increase, well, it increases throughout its entire domain. So the interval of increase is negative infinity to positive infinity. So there actually is no interval of decrease here. It's only increasing, and it's increasing throughout its domain. All right, let's do a few transformations. Here we have our parent function with a handful of anchor points to help us do this translation. So just like the other functions that we have worked with, when you add directly to the x, we're adding 3, so that means we are going to go to the left 3 units, since we are adding 3 to the x. So let's start. I'm going to take this 0, 0 point, and I'm just going to move it over 3 units to the left, so it'll go to negative 3. The next point I'm going to move is this point 1, 1. So if I move it to the left 3, that means I need to subtract 3 from the x. So I'm at negative 2, 1. And then I'll move this negative 1, negative 1. Come back up to this 2, 8. And then 3, 27. And I can put this point right here. There's room. So negative 2 moves over to negative 5. So that would be right here. And then down 8, which gives me this curve. For this transformation, I'm going to move over to the right one. So that moves me to the right one. Then I will reflect over the x-axis. And then after that, I will go up to, let me go back to my anchor points, and I like to start at 0, 0. So at 0, 0, I'm going to move to the right 1 unit, reflect over the x-axis while I'm on the x-axis, so I'll stay put. And then move up to next point, 1, 1. So starting at 1, 1, I'll move to the right 1, reflect over the x-axis, and then I'll move up 2. All right, next point, I'll do 2, 8. So at 2, 8, I'll start by moving to the right 1, reflect over the x-axis. So right now I'm at a y coordinate of negative 8, and then I'll move up 2 to be at a y coordinate of negative 6. Then 3, 27. So at 327, I'm going to start by moving to the right one. Then I'm going to reflect over the x-axis. So I go to where y is negative 27. And then I'll move up 2 to where y is at negative 25. For negative 1, 1, I'll start with moving to the right one. And then I'll reflect over the x-axis. So that will bring me up to positive 1. And then I'll move up 2, which would take me up to positive 3. And then at negative 2, negative 8, I'll move to the right one, reflect over the x-axis, so now I'm up at positive 8, and then I'll move up 2 more to get right at 10. Then at negative 3, negative 27, I will start with moving to the right 1 unit. Then I'll reflect over the x-axis, so I'm up at a positive 27. And then I'll move up 2 more to get up to positive 29. All right, that gives me this curve right here. Comparing parent functions. So here we have the quadratic function and the cubic function. The quadratic function is f of x equals x squared, and the cubic function is g of x equals x cubed. So the quadratic parent function produces this parabola where the cubic function has this curve. So let's look at the things that they have in common. They're both polynomial functions. They both have a domain of all real numbers, everything from negative infinity to positive infinity. They both have the same x and y intercepts at 0, 0. They're both increasing from 0 to positive infinity. So in that first quadrant, they're both increasing. They both have the same transformation patterns. In other words, if you add a number to the x, the function will move left. If you subtract a number from the x, you're going to move to the right. Vertical translations and stretches and reflections, they all work the same way. Also, both functions are continuous. Now let's look at some of their differences. The range of a quadratic function does not include any negative numbers. It's just 0 and including 0 to positive infinity, whereas the cubic function, its range is from negative infinity to positive infinity. It's all real numbers. Quadratic function has an interval of decrease from negative infinity to the quadratic function has an interval of decrease from negative infinity to 0. Whereas the cubic function, it does not have an interval of decrease, but its interval of increase is throughout its whole domain. So they're both increasing from 0 to positive infinity, but the cubic function is actually increasing more than that. It's increasing from negative infinity to positive infinity. Whereas the quadratic function, it has an interval of decrease. And then the end behavior. So in the quadratic function, you can see both ends are headed towards positive infinity. But with the cubic functions, as f of x approaches negative infinity, y approaches negative infinity. And as x And then let's look at end behavior. So both functions have the same right-hand end behavior. As x approaches positive infinity, y is approaching positive infinity. The difference is for the quadratic function, as f of x approaches negative infinity, y is approaching positive infinity. But with a cubic function, as x approaches negative infinity, y is approaching negative infinity. All right, that's it for this video. Thank you for watching.